and the output appear. There's no time delay between the presentation of the input and the response of the network. So it's instantaneous. Whereas the way you train the weights in MLP is iterative, because you start with some random initial weights and keep on training the network using backprop, and the weights change slowly and go towards a minimum of the error function, the output error function. So in Hopfield network is slightly opposite. The state update is not instantaneous, but it's iterative, because you start with some initial state, call it V naught, and work through the update tool, and finally you get some final state at some time instant t. Whereas the weights update is not, there's no training as such, you just calculate the weights based on the patterns you want to store, so that is instantaneous. But later on, we'll also look at a training algorithm where weights are also trained gradually, because that's more natural, that's more realistic from a real brain point of view. So we'll look at that later on. Because the original Hopfield network model proposed by Hopfield in two papers, 1982 and 1984, this is how they were formulated. So I'm just starting with that. So here again, the state update has again two forms, just like for the matrix. For the Hebb's rule, you have two forms, single element form and matrix form. For the state update also, you have a single element form and some kind of a matrix form. The single element form is what we have seen before already. Vi at t plus 1 is given as sigma, the sigma function of sigma j to n of wij vj at t. So given t, you calculate the state at t plus 1. If you want to do the same thing for the entire vector of states in one shot, then it looks more elegant. So sigma function of the weight matrix W times the state V at t. So it's very simple. This is and this is also faster. So now we can easily show that when you store only a single pattern S, and that S is a stationary state, that means if you start from S, you'll stay there forever, which is the minimum requirement, right? So if this is a stored memory, and right, and if you start in its neighborhood, if you're supposed to go towards it, all right, so that's a desirable property of the memory. But the basic minimum that you need is, if I start at that memory itself, then you have to just stay there. That's the minimum, right? Because stability is something more than that, but you need at least stationarity. So that is very easy to verify, because if you look at this update rule, V of t plus 1 is equal to sigma of W times Vt. So now so this can be written as, if you plug in this expression here, okay, so you have 1 by n and SS transpose times Vt. Now consider the initial condition, V naught is equal to S. I am starting at V equal to S. So then plug this in here. So you get sigma of 1 by n times SS transpose times S. So S transpose S is the inner product. SS transpose is outer product of two vectors and you get a matrix. But S transpose S is the inner product, so you get a scalar. So since SI is plus or minus 1, right, S transpose S is basically sigma, right, S square. Okay, so sorry, yeah. So that will be equal to n, because each SI is equal to plus or minus 1. So therefore you have sigma of 1 by n times Sn. So n gets cancelled. So you get S. Now S is plus or minus 1. Each of them is plus or minus 1. So sigma of that, since sigma is sine function, gives you S. So basically V is equal to S. Then this network stays there. The update doesn't change. So therefore you can easily show that V equal to S is stationary. So you get the logic of what's happening with this with this weight matrix. When you calculate the weight matrix using this Hebb's rule, right? We kind of pulled the rule out of the blue. We didn't say how it has come and all that. We kind of gave some mathematical justification. There's some motivation behind why W is chosen like this. But here you can see what happens when you choose W like this and how you get this kind of stationarity when you choose W's like this. Now, the original motivation for Hopfield network has come from not neuroscience, but it has come from the physics of magnetic materials. So for some reason, these magnetic systems are called spin glass systems, because magnetic particles have, the atoms are like have a spin, and that is what gives them the magnetic property. And they're arranged in a crystal lattice. So each atom has a spin. We can call and have two values, +1 and -1. And so if you look at this as some particles with some spin in a magnetic material, a given particle might be pointed in towards left or right in the spin of 1 or -1. Now, if the whole magnet is magnetized, right, then on an average, all the spins are pointed in one direction. So you have North Pole and South Pole. Now, the spin of a given atom is influenced by the spins of the neighboring atoms. So they can tend to coerce each particle towards the average spin of the neighborhood. Okay, and so the analogy here is that just as a particle has a spin of +or-1, the neuron has two states, the resting state and the excited state. Okay, and just as the neighboring particles coerce the state in a given atom, right, to change its spin towards the average of the neighborhood, a bunch of neurons will coerce a neuron to which they are connected, right, towards a state that is determined by their own states and also the connection strengths, whether they are inhibitory or excitatory. So similarly, another thing that happens here is so this interaction of the spins is given by some expression like this in the magnetic materials, and it is also shown that there is a potential energy function which is called the Hamiltonian, right, which is given in terms of the spins and the interaction coefficients Wij. And this energy, the system will tend to go towards minima of this potential energy. So once it goes there, it will remain stable. It remain there. It remains stable. So because of that, the whole material will be divided into small regions, which are called domains. And within a domain, most spins are in one direction. Okay, and so this is the property of magnetic material, which is used in their usage as memories, as magnetic memories in a hard disk. Because in a hard disk, you have the small domains where the spins are oriented in some direction, and you can use your head of your disk writer, to change these directions towards one or the other. So you can, if you want to, so that is what contains the bit value as 1 or 0. Let us say left is 1 or sorry, 1 or 0. So one direction is 1, the other direction, opposite direction is 0. So once you write it, it will remain there for a long time. So because it's stable. So this is how magnetic memory works. So Hopfield saw the analogy between such materials and brain, and he saw how brain could be storing memories, just as a magnetic system can store memories in the form of spins or average spins, which are stable states, right, of the material. Okay, so that's a great analogy, and so that's interesting. So it shows how you can borrow ideas from one field and carry them over into a very different field. Okay, so the thing is, so Hoppild's paper came in the 80s, right? But the idea of Hebbian learning didn't start with Hopfield. So what Hopfield has done very successfully in his model is to take certain very disparate things. So let me write it here. In Hopfield network, right? Hopfield network. You have the Makallo and Pitts, right, neuron model, which is a reasonable neuron model. It's not very realistic because we have seen what very realistic neuron models look like. So he has taken that. He has taken Hebb's rule. Hebb's rule is actually not proposed by Hopfield. It was proposed by Donald Hebb. I'll talk about that in a minute. Right, and he's looked at this, taken this network structure. Right, and because in a brain, neurons are connected so that everything is connected to everything. There's a lot of recurrence in the brain. So he has used that kind of a thing. And he has used the idea of an associative memory, which is a standard way to describe how memories are stored in the brain, or how memories are used, how human memories are organized by association. So he has taken all these aspects of human memory from different sources. He has taken a neuron model, taken a learning rule which is proposed by psychology, which just come from psychology. The network structure, which is again from neuroanatomy, the associative memory functions, which again comes from psychology, is put them all together into a simple, beautiful model. And that's why this model was very successful when it was first proposed in the early 80s. So the thing is, like I said, this Hebb's rule did not come from Hopfield. It was proposed by Hebb in a book called Organization of Behavior, which was published in 1949. So it was long before Hoffield's paper. So in that book, Hebb proposed or hypothesized that how memories could be stored inside connections of neurons. So what he specifically said is, when an axon of SLA is near enough to excite SLB, or repeatedly or persistently takes part in firing it, some growth process or metabolic change takes place in one or both cells, such that A's efficiency as one of the cells firing B is increased. So basically what he's saying is, suppose I have a neuron here, call it neuron A, which sends out a synapse to another. So synapse is in this direction. This is synapse B. Okay, so A fires, and then all that happens at the synapse, and you have PSP that is generated here and goes to cell B and changes voltage. And if the voltage crosses a threshold, B itself will get excited and it will fire another action potential. So this may or may not happen, depending upon many things, and we have already discussed all that in the first part of the course. So let us say there are two neurons A and B which are currently in a state such that when A fires, B fires very often. Okay, if that is the case, then something happens at the synapse in such a way that the synaptic strength increases. Okay, so that's what he's saying. In more simple language, when two neurons are simultaneously active, the connection between them must be strengthened. That's what this previous sentence is saying. And contrarily, if A fires and B doesn't fire or fails to fire, then if that happens repeatedly, then this connection strength between the two must be weakened. Okay, so this is what is more popularly described as neurons that fire together, wire together. Now we can take an analogy of this to more human and social context, just to understand this more intuitively. It's very similar to how we form friendships. Right, suppose you want to form friendship with you are A and you want to form friendship with B, right? And you go approach B and say, "Hey, shall we go for a coffee? And I want to talk to you," or something like that. If B responds and you guys go to coffee and discuss about everything under the sun, and you have a lot of shared interests and things like that, then the bonding between the two will grow. So the next time when you again ask for coffee, B has greater likelihood of responding and coming for coffee. Okay, so whereas you ask for a coffee and B says, no, don't want to go with you and things like that. Then if that happens even a few times, then you get kind of irritated. And after that, a bond between the two will weaken. Okay, so it's a very familiar experience in a human social context. You can just imagine that, take that as an analogy, right, to understand what might be happening at the level of cells. So I have had an insight to guess that something like that might be happening at the level of single cells in the brain. And much later, there is, well, actually, even before, there was experiments by Pavlov, right, a Russian physiologist called Pavlov, has performed certain learning experiments on dogs, and these experiments probably have kind of prompted Hebb to come up with this hypothesis. So the Pavlov's dog experiment goes something like this. So originally he was not studying learning in animals or anything like that. That was not Pavlov's objective. He was studying how digestion works in animals. But accidentally, some of the experiments have led to some very interesting experiments in learning. So Pavlov became famous for his learning experiments and not for his work on digestion. So what happened was, so when you in this experiments, when dog is given some meat food, right, and obviously dog has an innate instinctive behavior to salivate in response to the presentation of the food. So they call the presentation of the food unconditioned stimulus, and the response of the animal, of the dog, which is to salivate, the unconditioned response. So this is innate, and you don't have to train the animal to do this. So then after some time, whenever they present the food, they also ring a bell. So since the food is, the animal doesn't care about the bell because it doesn't have any meaning to it. But when the food is presented, it will salivate in response to that. But animal also notices that whenever the food comes, the bell also rings. So the two go hand in hand. So after that kind of a presentation, joint presentation of the bell and the food happens many times. Now the animal learns to associate the bell with the food. And next time when the bell alone is rung, the animals kind of expects that food also will come along, maybe very soon, if not at the same time, and will start salivating in response to that. So if you present food initially, what happens is, so you can draw the line here. So this is initial responses. And this is final after some training. So initially, when you present the food, the animal salivates. When you ring the bell, animal doesn't salivate. But during training, what you do is you present food and a bell simultaneously, and then animal salivates, but salivating because of the food, not because of the bell. After some time, so this part is training, and this is actually final. So this is training. Final means after training. So after training, when you present only the bell, the animal starts salivating. So salivation is unconditional response. The response to the bell is called a conditioned response because this response was not there originally, right? It was something that was learned by the animal because of this specialized kind of training. And the stimulus here, the bell stimulus, is called a conditioned stimulus because it's not the original stimulus, it's a special stimulus which is become important, which is able to elicit a response because of the pairing with the meat. The meat is called unconditioned stimulus, and bell is called a conditioned stimulus. Sometimes this bell is also called conditioning stimulus because it is what is conditioning the animal to respond to the meat. So this kind of a conditioning, right? They don't use the word learning; they call it conditioning. It's called classical conditioning because one of the oldest kinds of conditioning that was discovered. And for this work, Pavlov was awarded the Nobel Prize in 1904 for physiology and medicine. Now, this experiment, which is quite elegant and simple, can be accounted for using the Hebbian learning rule. Okay, so let us say I have a neuron here, okay, which responds to meat originally. Okay, so imagine of course, the dog's brain is very complicated, nervous system is very complicated, so many pathways and all that. But let us look at a simple schematic. So initially, there's a neuron which responds to the presentation of meat, and that leads to activation of some other neuron which controls salivation. So this is like I call this the salivation neuron, and this is a meat neuron. So when the meat neuron gets activated because of presentation of meat, that will send a signal. So this connection is initially very strong. It will send signal to the salivation neuron responds, and salivation occurs. Now I'll call this the bell neuron because this is what responds to bell. Imagine this is a part of the animal's auditory system. Now the auditory system neurons and the salivation neurons initially have no connection. The connections are all weak. So initially, if you just rang the bell, nothing will happen. It won't salivate. So now what you do is you repeatedly present, right? So this is the bell. Oh, shit. My artwork is pretty bad. Okay. So I repeatedly ring the bell and also present the meat. So then what happens? You're able to you have succeeded in activating the bell neurons, increase activation. You're also succeeded in activating the salivation neurons by presenting meat. So you cannot activate salivation neurons by itself, right? It's it's not easy. But by presenting meat, you are able to activate the salivation neuron. By ringing the bell, you are able to activate the bell neurons. Okay, so you keep on activating the bell neuron, salivation neuron repeatedly, and now the Hebb's rule says that if you do that, this connection becomes stronger. So after that, what happens is, even if you don't present the meat, because now your bell to salivation connection has become stronger. If you just rang the bell, salivation occurs. So this is a classical conditioning, and can be explained using Hebb's rule. Now, So the original classical conditioning experiments were behavioral experiments because they didn't take any recording from inside the brain. They just looked at the animal as input-output system. So input is meat and bell, output is salivation. So they had no idea. They had no idea what was happening inside the animal's brain. And the Hebb's rule, which was proposed in the late 40s and early 50s, right, also was a hypothesis. And they're also, even at that time, they didn't know much about what could be actually happening in the brain at this level of neurons. Now, those studies came in the 1960s. So one classic experiment was by Bliss and Lomo. Lomo, and this O. One of these O's has a strange kind of, I think it's some Norwegian guy. Okay, has a special notation there. So these people have performed some interesting experiments. So where they have taken, I think, a slice preparation. A lot of these experiments were done in hippocampus because hippocampus is a very important system for memory studies. So in this, they have isolated a synapse or a bunch of synapses, and they give some input firing activation to the presynaptic side, and also activate the postsynaptic side, and do that repeatedly, and see what happens to the synaptic strength. So activating the input side or the presynaptic side is amounts to basically giving a high frequency, series of impulses. So these are current pulses, which are like action potentials. So they give a high frequency series of current pulses on the presynaptic side. And on the postsynaptic side, activation means depolarizing, because when you give a strong input to the presynaptic terminal, and when it releases neurotransmitter and activates the postsynaptic side, the postsynaptic terminal, if it is an excitatory synapse, it will increase the local voltage. So that is equivalent to injecting positive current into the postsynaptic membrane and depolarizing that membrane. So increasing the activity of the postsynaptic side is equivalent to injecting positive current and depolarizing it, assuming it is a excitatory synapse. So they gave on the presynaptic side high frequency action potentials, on the postsynaptic side depolarization. If you do that repeatedly, what they found is after about 15 minutes of such joint activation of the pre and postsynaptic sides, they found that the synapse is strengthened. How do you verify that? So after that, it's like a crash course to the synapse for about 15 minutes. So if you do that, after that, if you give again a single action potential on the presynaptic side, you will see that the PSP, so initial, okay, so initial, the input is a single action potential. The output is a PSP, but a small amplitude PSP. So then you train. So how do you train? So this is the issue. How do you train? You give high frequency, lots of action potentials, high frequency ones. In response to that, you will have this tetanus and this build up, the temporal summation occurring, all that stuff. Then after that, after the training, right, what happens? So you give the same action potential on the input side. So this time you get a PSP, but it will be much bigger than what you saw before. Okay, so this is indication that the synapse is strengthened. Okay, so this kind of a strengthening of synapse is called long-term potentiation, because once it is strengthened, it becomes stronger. That increased strength remains for hours and sometimes even 1 or 2 days. So the idea is that this is the kind of change at the level of synapse or synapses that is occurring when animals learn something or when brains learn something, probably happening in humans also. This was a kind of indication that came out of those experiments. Now, there's also a contrary side to the experiment, just like in Hebb's rule. So you give high frequency action potentials on the presynaptic side, but on the postsynaptic side, instead of activating it, you deactivate it. So you give hyperpolarizing current or negative current into the postsynaptic membrane. So the membrane potential goes down, so it goes even less than -70, it gets hyperpolarized. When this happens repeatedly for about 10-15 minutes, the synapse becomes weaker. So which means, so initially it has, let us say, whatever response it has, and after that so this is initial, then you have training. Training is just like before, and then final. In final, when you give the same action potential, the response is even smaller than before. Okay, so and that low response will remain. So the synapses become kind of weaker on a long term. So that change remains for hours and even days. So this is called long-term depression. So they don't use the word learning because you don't want to just assume that this is what is happening in learning, because for that you need a lot more evidence. So these are preliminary experiments. So they just assume they thought, they gave a different term. It's called long-term potentiation. And the contrary experiment is the result is called long-term depression. So there are mechanisms by which at synaptic level you can increase the synaptic strength or decrease synaptic strength. Now, what is interesting is it is very similar to the Hebbian learning, because what is Hebbian learning saying? Okay, so what is Hebbian learning saying? So your Wij is equal to or is proportional to Vi and Vj. Okay, that means increase or make weight high only when both the input side and output side of the connection are high or positive. Otherwise, don't change it. Okay, but the thing is, the mathematical Hebb's rule was the way we formulated in Hopfield network has a small problem, because even when both are negative, you have -1 times -1, which gives you +1 for the weight, which is slightly a mathematical oddity. But otherwise, for all the other cases, when one is high, other is low, right? You get a negative weight. Otherwise, you get positive. So there are more variations of Hebb's rule, which are more realistic. But basically, it captures the idea. It is when pre and post are simultaneously active, you increase synaptic strength, otherwise decrease. This is the essence of Hebb's rule, and that is found to be true, really happening in synapses in these LTP, LTD experiments of Bliss and Loma. And subsequently, it's become a huge area of research, and even now it's an active area of research where people study, look for similar phenomena in various kinds of synapses in various animal species and so on and so forth. Also, people explore the molecular basis of that kind of LTP and LTD phenomena, and because of very complex molecular pathways, right, involving second messenger signaling and all that, which determine these kind of cellular phenomena, which is a huge research area. But I may not go into that. If I have time, maybe I'll take one class on that towards the end of the course. Okay, so we said we can store multiple patterns using a formula like this, right? The thing is, so suppose I have a 100 neuron network, and we can keep on storing patterns. So because we didn't say anything about any constraints on P, you can probably store many patterns. But that's what you would imagine. But in reality, what happens is when you try to store multiple patterns. So the thing is, when you store one pattern, things are very simple. But when you store multiple patterns, then things start, you get into trouble very quickly. That's the problem with Hopfield network. So, for example, even with one pattern, when you try to store a pattern S and you know that it's stable, there's another pattern which automatically becomes stable, that is -S. And why is that? That's very easy to show, because we already know that if S is a stored pattern, then it is stable. In the sense, it's stationary. Because okay, I'm using G notation here. It's it's same thing as sigma. So the next state is equal to sigma or G of WS. So we know that if W is equal to SS transpose, then this G of WS is equal to S. So that means S is stable. So if this is true, then just multiply both sides by -1, right? And we know that minus of signum function is signum of minus. Minus can be taken inside. So you can, if this is true, then we know very easily that this is also true, which means -S is also stable. Then, right? So which means if I'm storing a vector S and show that it is stable, its negative is also stable. And these states are called mirror states. So we wanted to make some states stable. In the process, we are also making some other irrelevant states stable. Okay, that's not the only thing. The other kinds of states, and the second category of states, which also become stable, which happens when you store at least 3 patterns. Suppose you have 3 patterns, S1, S2, S3, all 3 are stored patterns. You have stored them using the same Hebb's rule. Then consider this kind of a summation. Actually, consider more general kind of summation of the 3 patterns. I put a ±1 here also. and you calculate. So consider this vector S mix, which is given by signum of this summation. Then you can easily show that if n is large, tending to infinity, then S mix also can be quite stable. It can be it will be stable if n is large and all the patterns S are random. So I don't want to go into all these arguments, but you can very easily show this, which means that for large networks, even if I store 3 patterns, in addition to the mirror states, each of them will have mirror states, and minus S1, minus S2, minus S3 are stable. In addition, you have this huge number of about 8 patterns, right? All of them are also stable, which is not very good, but this is a property of Hopfield network. In addition, when n tends to infinity, you can show that you will have a large number of stored patterns, which are not correlated with the stored patterns at all, which has nothing to do with, because both the mixture states and the mirror states are correlated, the seed states are correlated with the stored patterns. But in addition, you have stable states which are uncorrelated with the stored patterns for large networks. These are called spin class states. So all these, you have so many other states which are not stored states, but which are stable. And all these irrelevant states, unnecessary states, are called spurious states. This is a big problem with Hopfield network. And because of the spurious states, as you keep on adding memories or trying to add patterns to the network using the Hebb's rule, you'll quickly reach a point when the retrieval performance becomes very bad. Because in addition to because if you have all these different regions, right, which are stable, okay, and so if I start from when close to a pattern, I should only land in that pattern. But instead of that happening, if it goes off to some other irrelevant state and lands there, then your retrieval performance is going to be affected very quickly. That's what happens in the Hopfield network. So if your number of patterns to number of neuron ratio is more than 0.138, which can be calculated using some theory which I'm not deriving in this course, then after that the degradation in the retrieval performance goes, happens very rapidly beyond this ratio. So Hopfield studied the same problem, but purely from numerical empirical point of view, just by doing lots of simulations, and found that for p/n ratio of greater than 0.15, the retrieval performance is very bad. Subsequently, people did some theory and showed that the exact ratio is 0.138, and beyond that, retrieval performance is quite bad. And you can easily see that this ratio is pretty low, because if I have, since it's a binary, these are binary vectors, I'm trying to store n bits, right? In a computer, if I have n bits, and that will give me 2 power n different vectors, okay, which is very high, whereas p/n ratio of 0.138 is basically p. So here p is equal to 2 power n, here p is equal to, let's say, approximately 0.14 times n. So this is for Hopfield network, and this is for computer memory, which is index memory. So index memory, if you have n bits, you can have totally p equal to 2 power n patterns. And Hopfield network, if you have n bits or n neurons, you can only store about 0.14 n patterns. So if you have 100 neuron network, you can only store 14 patterns. So which is terribly low. Thing is, why do we live with this? Why do we even consider this? So what we get, we lost something, but what we gain in the process is this property of content addressability. Right? That means even if you know a part of the content, you can retrieve the remaining part. That's what is special about Hopfield network. But with that extra advantage, you can only store only a small number of patterns. So you lose something and you win something. Whereas in case of index memory, which is what you use in computer, it doesn't have this property of content addressability. So given if you miss one bit, that's gone. You cannot retrieve the complete thing using partial information. So there are ways of improving performance, and lots of algorithms and learning mechanisms have been proposed to improve performance. One simple hack that is normally done is to set the self connections or self weights to 0 right? Because that will increase the chances. Because if you make it, this has to be positive. If you remember our derivation for proving that the energy function, right, always goes to the minimum, right, always goes down as update progresses. To prove that, we assume that the sulfates are all positive. But instead of giving them a non-zero positive value, we'll make it out 0. And why is that considered the extreme case where all the sulfates are all large positive numbers? Let's say they're much greater than 1 and much greater than all the other weights. So then you can think of, so what happens here if you do WII, so if this term dominates, right, in the update rule, when you do WII, this term dominates in the update rule. So you have G or WII, VIT, this term dominates in the summation here. So therefore, VIT plus 1 will be equal to VIT. Or take the extreme case where W is just the identity matrix I. So then if you do VT plus 1 is equal to sigma of W of V, which means I of V T, okay, so which is equal to VT. Therefore, state doesn't change. Okay, so which means that the weight matrix in which all the diagonal terms are positive and high, right, and much higher than the off-diagonal terms, it will tend to stabilize the state wherever it is. In the extreme case, when weight matrix is just identity matrix, every state in the state space is stable because wherever you are, you just stay there. That means of the two possible states, right, all the states are stable. So which is pathetic because the memory becomes completely useless when that happens. Okay, so that is what happens. That is some data about the original Hopfield network, which is a discrete Hopfield network. So then Hopfield also proposed a continuous version of it because the discrete version is somewhat unrealistic because time is a continuous quantity. So he proposed a continuous model in the subsequent paper in 82. So here the difference is you have a neuron and it has an input, it gets an output. In the previous case, the output is, in the case of discrete Hopfield network, the output is simply a function of the input. Okay, whereas in this case, output is not directly a function of input. The input controls an internal variable called U, okay, and U controls the output of neuron V. And the relationship between the input and the the internal variable U is defined by differential equation. So that is how you bring in this continuous time aspect of the continuous Hopfield network. Okay, so in the continuous model, you have a differential equation defining the dynamics. In the previous case, the discrete case, you have a difference equation, a discrete map that links the current state to the next state. So in the continuous model, this is how the model is defined. So there's internal variable U, for the ith neuron, it is UI. And the input to the neurons from all the other neurons is given by Wij times Vj, where Vj or Vi is output of the ith neuron. So Vi, hidden internal variable is UI, and there's a total input going in. Because this neuron receives input from all the other neurons. So this is, let's say, the jth neuron, and this is Wij. So the jth neuron over the weight Wij sends input to the ith neuron. So this is all those terms. And in addition, you can also have an extra input going to the ith neuron. So this is a differential equation which determines the relationship between the input and the neuron's dynamics of UI. And given UI, the output of the neuron, which is Vi, is simply given by a static function. So here the notation is G. G is not the signum function. Here they use a continuous function. So the tan h is like a continuous equivalent of the signum function, which is what is used here. And lambda controls the slope of the tan h function. And usually lambda is taken to be a large positive number. So and here also there's an energy function, which is a small extension of the previous one. So you have the original energy function, which is sum over Wij, Vi, Vj. In addition, you have a couple of terms. One term is integral of G inverse. So G is the tanh function. This is G inverse of V dV. This integral is done for every one of the for every variable, every neuron. And then you have the third term, which comes because of the external input II. So we can easily show that as this update progresses in time, this energy function goes to a minimum. So basically, the update is like performing a gradient descent over this energy function. You can easily show that, because if this is E, consider dE by dt, which you can show that is of this form. So sigma over n, and inside the brackets you have sigma of j equal to 1 to n. So the derivative of this expression, this quadratic expression, is wij vj, and for this we assume that wij is equal to wji, which is what we also assumed in the discrete Hopfield network case. Then this integral, right, if you differentiate that, so integral simply gives you integral. When you differentiate this, integral goes away. You get simply G inverse Vi, and that is nothing but Ui. So you get Ui here, and so you have minus sign going out. So that's why this becomes minus sign here, and this minus sign. So if you differentiate this with respect to time, you get dvi by dt, right, and which goes out of this expression. So you get this, and this whole thing inside the brackets is nothing but dui by dt, because that's your update equation. Okay, so if you plug that in here, you get sigma over n with the minus sign in the front, dui by dt times dvi by dt. Now vi is nothing but g of ui. So dvi by dt is equal to g prime of dui by dt. Okay, so therefore this is g prime ui by dt times dui by dt whole square. Now g prime is simply the derivative of the tanh function, which is always positive. Okay, so this whole expression is negative because of this minus sign here, which means that E always goes down, and E is bounded because all the terms inside this are bounded. So therefore, E decreases monotonically with time. Okay, so here also we can show that the single neuron model is stable. In fact, we have done this when we were discussing the simple single neuron models. This is the what I call the binary dynamic binary model, or a dynamic binary neuron model. And we can show that when lambda is sufficiently high, much is greater than 0, right? For a single neuron, we'll have two stable states. So we've already seen all this before. And okay, so when you have two neurons like this, then you can also show that that network has two stable states. So one is near, so if you store, like, for example, 1 minus 1, then again use Hebb's rule. The weight matrix, so if S is equal to 1 and minus 1, the weight matrix will be equal to 1 minus 1 and minus 1, 1. If that happens, you can show that you'll have two stable states, one at minus 2 and 2, other at 2 and minus 2, and all flow goes towards these 2 points. You can see that in this plot. And origin will be a saddle node, because if you approach origin in one direction, approach origin in one direction, you'll go towards it, and from there it will go away from it towards two stable states. So okay, let us stop here. In the next class, we'll look at the Cohen-Glasberg system, which is basically another extension of Hopfield network, where the weights are also trained gradually through time, unlike in the Hopfield network where they're just calculated using the Hebb's rule. And that kind of a model is now takes us closer to what people are thinking happens in the hippocampus and how memories are stored in the hippocampus. Okay, so let us take a break and let's again meet next week. Thank you.